Hello everybody. Today let us discuss how to solve the knapsack problem using dynamic programming. What is a knapsack problem? In knapsack problem, we will be given with n number of items or objects, each of which will have some associated weights and values. And we will be given a knapsack or a bag of some capacity W. The objective is to fill the bag with a subset of these objects such that the maximum capacity of the bag will not exceed, and also we will get the maximum profit. To solve this problem, basically what we have to do is we have to find all possible subsets of n objects that are given to us. Then we have to find out for each one of the subset what is the value profit that we are going to get, and the maximum one is the solution that we are looking for. So therefore it becomes a very tedious job for us to find all possible subsets of n items, because we know that if we have n items, then there will be 2 to the power of n number of subsets. Therefore, we apply dynamic programming to solve this particular problem in a much more efficient way. What is dynamic programming? Dynamic programming is an algorithm design technique which is suitable for problems which have overlapping subproblems. Basically, dynamic programming suggests that when you have a problem which has overlapping subproblems, it requires us to solve all the overlapping subproblems and store it in a table, so that the next time we need the value, we'll take the results from the table instead of recomputing it. Otherwise, in general approach, what we would be doing is we would be solving the overlapping subproblem again and again, and thereby the overall efficiency of the algorithm reduces. So let us understand how dynamic programming works when we apply to knapsack problem. So let us assume that we are given 5 objects and the maximum capacity of the knapsack is 4, and let us assume the weights and the values of these objects are, say, 2, 15, 1, 20, 2, 12, 2, 14, 1, 10. So let us assume these are the 5 objects that are given to us with weights 2, 1, 2, 2, 1 and values 15, 20, 12, 14, 10. We have a knapsack or a bag of capacity 4. We basically have to fill that bag such that it consists objects whose total weight is not more than 4, and also we get the maximum profit. So we'll have to find all possible subsets of this. See, we may form subsets of objects 1 and 3 which has a maximum capacity of 4, 1 and 4, 3 and 4. So 2 plus 1 plus 1 is also another subset, 2 plus 1 plus 1. So there are so many subsets whose capacity will not exceed the maximum capacity of the knapsack, and each one of them will have different profit. So therefore we have to find out all possible subsets, only then we will know which one will give us the maximum profit. So to solve this, basically what we do is, in dynamic programming, as we saw, we are going to create a table, and in the table we are going to store all the solutions of the smaller subproblems, overlapping subproblems. So the next time we need, we'll take it from the table instead of solving it again and again. So we'll construct a table in which the rows represents the items. Okay, so here we will have object. So first one will be 0, 1, 2, 3, 4, 5. So the rows represent the objects, meaning this row represents that we are selecting only 0 objects. This row represents we are selecting 1 object. Here 2 objects, 3 objects, 4 objects, 5 objects. So every row we are selecting those many number of objects, and we are trying to find out what is the profit that we are going to get. The columns will represent the capacity of the knapsack, and once again the capacity of the knapsack varies from 0 to whatever is the maximum capacity of the knapsack that we have. So therefore it will be 0, 1, 2, 3, 4, 5. Sorry, 4, because we have a knapsack of capacity 4. So it means that here we have a knapsack of capacity 0, here we have a knapsack of capacity 1, here we have a knapsack of capacity 2, 3, so on and so forth. So when we want a particular entry, say suppose if I want to know what does this mean, this entry in this particular two-dimensional matrix mean 2 cross 3. So it means that this entry will give us the maximum profit we get with 2 objects and when the maximum knapsack capacity is 3. Okay, so any entry we can take. So here this will tell us what is the maximum profit that we get when we have 4 objects and the maximum capacity of the knapsack is 1. So slowly as we proceed from one row to other row, we are going to add the next item into the knapsack and try to find out can we get a maximum profit by including that object or not. And as we move along the columns, we will be gradually increasing the capacity of the knapsack so that we can accommodate a new object. So obviously the last entry over here, this will give us the final solution. So this is the profit that we will obtain when we find subset of 5 objects and the maximum capacity of the knapsack is 4. So that is what is needed for us. We have 5 objects and we have a maximum capacity of the knapsack as 4. So therefore this entry will give us the result, that is what is the profit that we get when we have 5 objects, subset of 5 objects, which will give us the maximum profit for a knapsack of capacity 4. So one observation what we can make here is, so if we take the very first row, that is 0. So this is the profit that we are going to obtain when there are 0 objects. Basically there are no objects, so therefore whatever be the capacity of the knapsack, the profit that we are going to get will be 0 always. So therefore 0, 0 will be 0 because the capacity of the knapsack is also 0, objects are also 0. Here we have a knapsack of capacity 1, but we don't have any objects, 0 objects. Therefore this is also 0. Knapsack capacity is 2, no objects, 0. Knapsack capacity 3, no objects, 0. Knapsack capacity 4, no objects, 0. Okay. Same thing with the column we can observe. Here we are trying to include the objects, but we don't have a knapsack which can accommodate any of these objects. I have one object, but the capacity of the knapsack that I am considering is 0. So therefore I can't get any profit. 2 objects, no knapsack, 0. 3 objects, knapsack capacity 0, 0. 4 objects, knapsack capacity 0, 0. 5 objects, knapsack capacity 0, 0. So the first row and the first column will be zeros. The other entries needs to be computed, and finally we need to know what is the value that we get at the 5th row and the 4th column. Okay. So now how are we going to compute the other entries in this particular table? So if we can look at the table very carefully, one thing what we can observe is, firstly there will be 2 options. What are those 2 options? To fill any entry. It may be possible for us to include the next object, or it may not be possible, depending upon the capacity of the knapsack at this particular point. So now here the knapsack that we have has a capacity of only 1. This object will have some weight. Okay. So now if the weight of the object that we want to include is more than the capacity of the knapsack that we have, then obviously we can't include that particular object into the knapsack. So therefore in that case what we will do is, we will not include this particular object into the knapsack. So we don't include the object and we will retain whatever profit we get without including this object at the same capacity of the knapsack. So where will we get that? We will get it in the previous row, same column. So this entry is nothing but what is the maximum profit that we get by including one object, okay, this current object number 1 into a knapsack of capacity 1. If suppose the weight of this object is greater than the knapsack that is available, that is 1, then we can't include this. So therefore I will retain this. The maximum profit is same as whatever I could get when there were 1 fewer objects, that is 1 less than this, that is 0 objects, and the knapsack capacity was same. So that is the first option. Second thing is, let us assume that I am able to include this object into the knapsack. Once again, there is no guarantee inclusion of this object will give us the maximum profit or not. Okay, so we should see whether inclusion of the object will give us the maximum profit, or without including the current object, the previous selection itself will give us the maximum profit. So once again, there are two options. Whichever gives the maximum profit, that we have to retain, the other one we have to discard. So now if we can include this object into the knapsack, if we can include this particular object into the knapsack, then there must be enough space for us to include this particular object into the knapsack. Okay, this object will have some weight Wi, and let us assume that these knapsack capacities along the columns are represented by J. So now here the knapsack that we are talking has a capacity of 1. This object has some weight Wi. So now if I have to include this particular object into the knapsack, then there should be enough room in the knapsack for adding this particular object. So where will I know what is the maximum profit when there was enough room for adding this particular object? So to know that, I'll have to go to the previous row, because this object I have not yet included. So I will go to the previous row and I'll have to go to Wi columns backwards. Okay, so J, whatever is the J minus Wi. So whatever is the weight of this particular object, that much space needs to be made free to include this particular object. So therefore in the previous row, I will go Wi column backwards, whatever is the current capacity, that is J, minus Wi, whatever is the maximum profit, that value I will take, and to that I will add the value of this particular object, because now I am going to include this object into the knapsack. So I will get some profit because I have made the enough space, I have included this object, therefore I have added this weight to that particular value, I have got some profit. So that is by including the current object into the knapsack. If I don't include the current object into the knapsack, then I have to go to the previous row and the same column, because this is the capacity of the knapsack and this is the profit that I obtained without including this object, but with the same capacity of the knapsack. So between these two, whichever is maximum, that value I'll have to retain here. Okay, so let us fill this table so that we will understand it better. So if you can see, this is for 1, 2, 3, 4, 5. Okay, so first thing is, I told first we should see whether this particular we can fill the table either row wise or column wise. We will fill it row wise. So first let me try to fill this entry. So now here, first thing I want to make sure is whether this particular object can be included or not. So if I want to include object 1 into the knapsack, then there should be enough space for me to include the object. So what is the weight of this object? The weight of this object is 2, but the capacity of the knapsack is 1. So therefore you can't include a object of weight 2 into a knapsack at this point of time whose capacity is only 1. Okay, so therefore I will conclude that I can't include this object. Therefore without including this object in the previous row, whatever was the maximum profit, that itself will be the maximum profit now also. So therefore it will be 0. Previous row, same column. I'll come here. Now I will try, I have increased the capacity of the knapsack to 2, and now I will see if I can include this particular object. So the weight of this object is 2. I can include into a knapsack of capacity 2, but I should have enough room to include this particular object. So when I have not included this object, I will go to the previous row, that is the 0th row, and I will see what is the profit that I got when I had enough room to include this particular object. That is 2j minus wi. From this column, wi columns backwards. What is wi? Wi is 2. 1, 2 column backwards. So without including this object, the profit that I got was 0. Now if I include this object, then I will get a profit of 15 additional to whatever value I have here. So 0 plus 15. So here 15 is the profit that I get if I include this object. If I don't include this object, what is the profit I get? I will have to go to the previous row, same column, because in the previous row, in the same column, I have the same knapsack capacity. I am not including this object. What is the profit I get? So the profit I get is 0. So which one is maximum out of 15 and 0? So profit of 15 is more by including this object. Therefore I will retain 15. Okay, same way I will fill the other entries. I will come here. When I come here, the knapsack capacity is 3 and weight of this object is 2. I can include, so I will go 2 column backwards. Here I had 0. So 0 plus including this object, I will get a profit of 15. Without including, I will get 0. Okay, which is maximum? 15 is maximum, I will retain 15. So same way this will also be 15. We will go to the next row. So here when we come, once again, here I have the maximum profits when I am including the first object into knapsacks of capacity 1, 2, 3, 4. So now here I want to see whether I can include the second object. When I want to include the second object whose capacity is 1, I can include because the knapsack capacity is also 1. But for that, if I want to include, I will have to go to 1 column backwards. So I will go back here and I will see the profit was 0. To this 0, if I add this object, I will get a profit of 0 plus 20, that is 20. If I don't include this object, then the previous row same column, the profit will be 0. So maximum out of this is 20. So therefore, I will retain this 20 as the maximum profit. When I come here, if capacity is 2, weight is 1, I can include. I have to go 1 column backwards. 0 plus 20 is 1 option, that is if I include this object. If I don't include this object, then the maximum profit I get is 15. So maximum out of 20 and 15 is 20. So I will retain 20 here also. When I come here, once again capacity is 3, weight is 1. From here onwards, it is possible for me to include the object into the knapsack. So therefore, I will go 1 column backwards because I need to make enough room. 15 plus the current object, that is 20. 15 plus 20 is 35. If I include the current object, if I don't include, then it is 15. So 35 is maximum. So I will retain 35 and I will leave 15. So same way here also when I come 1 column backwards, 15 plus 20, 35, comma 15, that is 35 is the maximum profit. So this row gives me all options wherein I have 2 objects, a subset of these 2 objects which will give these profits depending upon the capacity of the knapsack. So third row, I want to include the third object. So here once again I will see the third object weight is 2, but the capacity of the knapsack is 1. It is not possible for me to include that particular object. So therefore whatever is the maximum profit without its inclusion, I will retain as it is 20. When I come here, the maximum profit is 20. Sorry, weight is 2 and here also we have 2. So now I will see, I will go back 2 columns to make room to include this particular third object. Okay, the profit at that time was 0, and if I include this third object, the profit that I get is 0 plus 12. Okay, if I don't include this object, then the maximum profit previous row same column is 20. So now you can see, even though you have an option to include the current object, if you include the current object, you won't get a better profit than not including it. So therefore, we will settle for this option, that is I don't want to include the current object because without including it itself, I am getting a better profit. Okay. So again I will come here. When I come here, 20 plus 12. 20 plus 12 is 32. So 32 is the maximum profit I get if I include this object. If I don't include this object, I am going to get a profit of 35. So once again you can see, even though you can include the object, this knapsack also has both these objects, the object 2 and object 1. Okay, but it gives a profit of only 32. But if you skip this object 3 and if you retain only the object 1 and 2, then you will get a maximum profit of 35. So therefore you are going to retain this value of 35. Again we will come here. So now I can include 2 columns backwards, 20 plus 12. Again by including the current object you will get a profit of 32. Without including it you will get 35. So I will retain 35. Okay, same way we will fill the other 2 rows also. Capacity of the knapsack is 2. Capacity of the knapsack is 1. Weight of the object is 2. Not possible to include. So therefore 20. So here when we come, I can include, so 2 column backwards, 0 plus 14 is 14, without including it is 20, so therefore maximum is without including 20. So here once again 2 columns, 20 plus 14 is 34, okay, 34 and this is 35, so without including itself I will get a maximum profit of 35. Then again here 2 columns 20 plus 14 is 34 without including is 35, which is better, so I will retain this 35. Okay, so now here when we come here, the capacity of the knapsack is 1, weight of the object is 1, 0 plus 10 is the maximum profit I get. Without including the current object, I will get a better profit of 20. Here 20 plus 14, 34. Okay, so if I include the current object, then I will get a better profit. Without including the current object, I am getting a profit of 20. By including, I am getting 20 plus 14, that is 34. I will retain this. Here, one column backwards, 20 plus 14 is 34. This is 35. Without including itself, I get a better profit, 35. Finally, here, 35 plus I include this, 45. If I include this, I will get a profit of 45. If I don't include, I will get a profit of 35. So, if I include, I will get a profit of 45, which is better than the previous one. So, therefore, this is the final answer. So, the optimal subset will give me a profit of 45. Okay. So, this is fine. Now, if I have to know what are the elements that were included into the knapsack, because information about that is lost when we were calculating this. We just concentrated on the maximum profit and we didn't keep track of which objects were included and which objects were not included. So how do we find out which objects constitute the subset whose maximum profit is 45? Okay, so once again for that we will have to apply the technique in the reverse fashion, whatever we apply to calculate these values in the table. So now this value in any cell in the matrix will depend on two other values. One is the value in the previous row same column, or in the previous row this wi column backwards, to which we added this. Okay, so therefore it depends on these two values. So we will have to concentrate on those two values in the previous row, and if this value is equal to the value in the previous row, it means that the same value was copied and therefore this object was not included. Okay, only then see like this. Here 35 came from here, and which means that this object was not included. But here 45 is not equal to 35, so therefore it means that the new value is added here. Therefore the fifth object is included in the knapsack. Okay, then we will have to go to the previous row. Where we will go to the previous row? From where we added this object, where we added one column backwards. So we will come here. So this leads here. So 35. So now to come here, we would have come either from here or two columns backwards from here. Okay. Now if you see these two values are same, so therefore this value was taken from here, and therefore the fourth object was not included in the knapsack. So to come here, I came from here. So now once again I will repeat the same process. To come here, I should have come from here or two column backwards from here. So if I see these two values are same, therefore I should have come from here. So I will go back here. Okay. And now once again to come here, I should have come either from here or one column backwards from here. So these two entries. So if I see these two values are not same, so therefore I should have come from here. Okay. So now this object was included, object 2 was included. Okay. And now if I see this and this entry, these two are not same, therefore this also must have been included, and I came from here. So now if you can see, you start from the leftmost entry in the matrix and you go to the rightmost entry in the matrix. Okay. So therefore these are the objects that are included: the first object, second object and the fifth object. The first object, the second object and the fifth object. 20 plus 15, 35, 35 plus 10, 45. So this is the maximum profit that we got, and these are the elements that constitute the optimal subset. Okay. So if we can see, we can write an algorithm in a bottom-up approach, because there is a two-dimensional matrix that we have to fill. Okay. And we can have a for loop which will keep track of the number of items for I is equal to 1 to n, and we can keep a inner for loop which will keep track of the columns, that is the knapsack capacity increasing starting from 0 to W, okay, and we can find out each one of the values by applying this formula, okay, based on the conditions that I told. If the capacity of the knapsack is less than the weight of the object, then from the previous row you retain as it is. If it is more, then again we have two options. What are those two options? Whether to include the object or not include the object. If you are not including the object, it is very simple, retain the value from the previous row as it is. If you can include, then in the previous row go Wi column backwards, to that add the current value of the current object, and then see among these two which one is maximum. Just going backwards doesn't mean that we are taking. After adding, we will check which one of them is maximum, and only the maximum one we are going to retain. Okay, so now if there are n number of objects, okay, n number of objects, and the maximum capacity of the knapsack is W, then there will be n plus 1 number of rows, because we have a 0 over here, n plus 1 number of rows, and W plus 1 number of columns. So we will have a matrix of size n plus 1 into W plus 1. Okay, so when we multiply this, we will get it as n into W. We will leave these lower order terms. So therefore, the efficiency of this knapsack problem will be n into theta of n into W, the number of rows and number of columns. It is as simple as calculating the number of entries in this particular two-dimensional matrix, because all the entries needs to be computed to find the optimal solution. Okay, so basically here we saw that the matrix was filled in a top-down bottom-up fashion. We started from the first row, first column, and then we moved towards the nth row and the wth column. Okay, so and also if you can observe these boxes over here, we will get to know that only these values were needed for us for finding the optimal solution, and the other entries were not at all needed for us. But we had to compute those values because we came in a top-down bottom-up fashion, wherein we computed all the entries and finally we arrived at this particular entry. But in a big problem, when there are more number of objects and the capacity of the knapsack is more, then computing all these entries which are not required will waste our time. So how can we improve the efficiency? To improve the efficiency of this, we are going to use the concept of what is called as memory function. Okay, so basically if we develop an algorithm which works bottom up, this is how it works. But if you can see, if we can write an algorithm which will be top down, that is we write a recursive function in which the recursive call will be made for n objects and of knapsack of capacity W, then it will know which entries it needs and it will compute only those entries. This needs these two, it will compute these two. This will need these two, it will compute. So only those values that are needed will be computed, and all those values that are not needed will be left out. But the major drawback with the recursive functions are that the recursive functions will recompute the overlapping smaller subproblems again and again, and thereby reduce the overall efficiency of the algorithm. Therefore, the memory functions will combine the advantage of both the top-down approach, the recursion, and the bottom-up approach, that is the filling up of these tables. Okay, how does it do? So basically in memory functions, what we do is we will have the table like this, and we will write a recursive function. The recursive function basically will call with the value n comma w. Okay, and it will know only which entries to compute. So now to compute only those entries that are needed, what we basically do is we will fill the table with an null values. Okay, it means something like -1. -1 indicating that these values are not yet computed. Okay, so when we give a first call to it, it will come here. It needs this 5, 4. So when it wants this 5, 4 and it sees that this entry is not yet computed, it will find out which values it needs to know the value of 5, 4. Then it will zero in on two entries in the previous row and it will check whether that is computed. Okay, and if it is computed, it will take the value. If it is not computed, once again to know these values, which entries in the previous row needs to be computed. In this particular fashion, it comes backwards and it comes to the first row and first column, as we know, which are already known. From there, it will just fill the table just like a bottom-up fashion what we did, and it will compute only those entries that are needed, and finally it will return the value that is needed for us. One thing what we can observe here is, once again the order of growth will not change. The order of growth is n into w itself, because in the worst case it will have to fill all the entries of this particular matrix. But actually what happens is, since it will not compute all the entries of the matrix, the running time will be less. The running time will be faster than a bottom-up approach, but the efficiency class is still n into w. Okay, so let us not compute the table, because as I told you, the call will be a recursive call in a top-down fashion, but the table will be filled in a bottom-up fashion. We will see only the algorithm, okay, and we will see how it will fill this particular table. Okay, so this approach of combining the top-down and the bottom-up is called as memory functions. Okay, using memory functions. So we will call this algorithm as memory function knapsack. Okay, I objects, j knapsack capacity. Okay, if we will call the two-dimensional matrix by a name called as k, the kth entry of I comma j, okay, is less than 0, which means that it is not yet computed. Okay, ith object and the jth column, if it is not yet computed, then we need to compute. When we need to compute, what is the first thing we do? First thing we do is we will see whether the current object can be included or not. Okay, so for that, the capacity of the knapsack must be more than the weight of the object. Okay, so if wi is greater than, if wi is less than j, okay, means the weight of the current object is less than the capacity of the knapsack that we have, then only I can think of computing the values. Okay, first I will tell, if wi is greater than the current capacity of the knapsack, then what I will do is I will take the value from the previous row, same column, that is mf knapsack I minus 1 comma j. Okay, I minus 1 comma j in the previous row, same column. Okay, else suppose the weight of this object is less than the knapsack capacity. Once again, then I have two options. Okay, what are those two options? Value is equal to maximum of, one is I include the object, other one is I don't include the object. If I include the object, then it is value of the current object vi plus mf knapsack in the previous row I minus 1 j minus wi. Okay, so this is, I am going to include the current object. To include the current object in the previous row, I need to go wi columns backwards. Okay, that is one option I get. Or the other one is, I am not going to include the current object. In that case, I am going to take whatever value is present in the previous row as it is. So that is mf knapsack I minus 1 comma j. So among these two, whichever is maximum, that will be taken. Okay, it will be computed, and finally whether this value or maximum of this value will be written in that particular entry, k of I comma j is equal to value. Okay, so in this particular fashion, if you can see, there is a recursive call. The function calls itself by going to the previous rows. First it starts with I. Okay, the initial call will be with n comma w. Okay, so that n will go to n minus 1, and this j, if required, it will go to j minus wi, or the current, the same value of j, and whichever is maximum it will compute. And finally, once everything is computed, it has to return the optimal value, return knapsack of n comma w. So this is the maximum profit. Okay, so that is the value that we are looking for, and that value will be returned. Okay, and similarly you can have a function for finding the objects of the optimal knapsack by comparing the entry in the current row with the entry in the previous row. If both of them are same, then the current object is not included. If both of them are not same, then the current object is included. In the previous row where you have to go WI column backwards. Okay, again compare. Once again you can call the same function and you can revert back, come in a reverse fashion to know which objects were included in the knapsack. Okay, so we can see that dynamic programming is a very good. Knapsack problem can be solved using many other algorithm design techniques also, but dynamic programming is one good approach because it can be applied for overlapping subproblems, wherein the overlapping subproblems can be solved only once, stored in a table, and those values can be taken later when they are needed. Otherwise, in a top-down approach like a recursive call, the functions will be called again and again repeatedly, the overlapping smaller subproblems, and time will be wasted in recomputing them many number of times. Okay, so therefore the dynamic program approach for solving knapsack problem is a reasonably good algorithm. Thank you.